Okay, this is the third lesson from the week April 20th through the 24th, and we are now going to be talking about solids, and we're going to be looking at one particular type of solid, which is called a crystalline solid. Just so you know, there are other types of solids. There are things that are called amorphous solids. Something like a rubber band would be an amorphous solid. There's all sorts of in-between type of uh, materials which aren't quite liquid or solid. And so this is an elementary course, and we're going to deal with the most common type of solid, which is called a crystalline solid. What we mean by a crystalline solid is that it is a solid where its constituent parts, the things that form the solid, arrange themselves in some sort of regular pattern. So there is a regular pattern or a regular arrangement of the constituent parts. I don't think I spelled that right, but the constituent parts of the solid. Now, I usually wouldn't use a word like constituent parts, but constituent parts means the parts that make up the whole. And what's interesting is that the way we're going to classify the solids will be by what their constituent part is, and you'll see that here in a second. Let me show you, though, a solid. You've already seen this one before. This is actually a fairly good model of sodium chloride. The sodiums would be the green, the chlorines would be the sodium would be the blue. This is an ionic solid, and we mentioned before that an individual sodium chloride would be that. It would be a sodium atom attached to a chlorine atom, but actually a sodium ion positive attached to a chlorine, which is negative. But when you start putting them all together, they're going to lock into some sort of shape. This is called a cubic crystal. There are other types of crystals. There are ones where you have a more complicated pattern. If you've ever seen a quartz crystal, or perhaps you've seen some of those rocks that they break open and you have crystals inside. If you have you probably don't, but if you have Epsom salt, magnesium sulfate, it's called Epsom salt at home, and you look at it, it has a crystal which is six-sided and elongated. And there's all sorts of different types of crystals. If you were at school, I have a number of them that rather than throwing away chemicals, you may have noticed this, I let them slowly dry, and in the process of doing that, they will form crystals. There's another type of crystal. This one would be a water crystal, which we would call ice. What you've got are the partially negative side, which is red, two partially positives, and those will arrange themselves in some sort of pattern as well. It's a little harder to see, but you can see what's happening. That white attaches to the red, this white attaches to a red, this red attaches these white and red attach, and we end up with some sort of a crystal. And a lot of you would know that, of course, a snowflake would be a water crystal. I wish I could show you all the different types of crystals, but it's just not possible without being in school and seeing them. You could probably look them up online. There's 7 different types of crystals, but we're going to look at the basic different types of crystalline solids. So we actually can do a chart that looks like this. When we talk about crystalline solids, we can have an ionic solid, and we can have a molecular solid, and we can have an atomic solid. So ionic solid, molecular solid, and atomic solid. The constituent part part on this one is the ions. Makes sense. It's an ionic solid. Anyone want to guess what the molecular solid's constituent part is? Yes, of course, it is a molecule. And for an atomic solid, it is an atom. The easiest one to understand is the ionic solid. It's this one here. It's the one that you saw. What you have are positive and negative ions, which form the bond between this green and this blue, or this blue next to it, or any of the blues next to it, is the same bond. So in a sense, this is all intermolecular or intramolecular forces, although we wouldn't call them intramolecular forces. Unlike a molecule where you have bonds that are holding the atoms together and then smaller or lesser bonds that are holding the molecules, it's the same bond which holds this whole block together. And so when we talk about this, the constituent part, the force that's holding it together is the positive ions attracted to the negative ions, or vice versa. It is a very strong bond. And as a result, we would say the stronger the bond, most ionic solids have very high melting points. Now, when I say that, there are exceptions. Sodium chloride, the melting point is about 2,000 Celsius, but something like potassium chlorate, the melting point is just a little over 100 degrees Celsius. So there's different ones, but that would be that. And then ionic solids always conduct electricity. They tend to dissolve well in water. Molecular solids are held together by molecules. These are held together by the intermolecular forces. And intermolecular forces here are much weaker than the ionic bonds that are holding this together. And as a result, we expect that you have lower melting points. And by the way, the size of the molecules would make a difference as well. Sugar, a lot of you may have done this little simple science experiment when you were kids. If you take sugar and saturate it, put as much as you can to get it into water, and then put a string down in it, you'll grow beautiful crystals. Put some food coloring in, you can grow some really amazing ones. And yet, if you go to melt sugar, it has a very low melting point. Now, I'll come back to the atomic solids here in a second, because that's actually where I want to spend more of my time. But let me explain what's going to happen. When we have intermolecular forces, if you remember, we have three types of molecules, three types of forces. We have nonpolar molecules, and those are called London dispersion forces, or just dispersion forces. We have polar molecules, in which case we have dipole-dipole, and we have hydrogen bonds. Whenever we have a hydrogen-oxygen, hydrogen-nitrogen, or hydrogen-fluorine bond, we have hydrogen bonds. What will happen is these become stronger as they go. But at first you might ask, how in the world do we have non-polar molecules forming bonds? And as I mentioned before, if I take something like hydrogen, which is sharing 2 electrons, at any point in time, you will have one end be more negative than the other. In fact, the polarity is switching back and forth between positive and negative. If I put that next to another hydrogen atom, which is also positive, negative, switching back and forth, and another one down here, where we have this switching back and forth, positive, negative. And by the way, it's not partially positive, partially negative. It's truly positive or negative. It's just for a very short period of time. You get enough little connections between here that eventually, if you get the temperature low enough, a nonpolar molecule will eventually become a liquid and then eventually become a solid. The only exception is helium. As far as I know, they have never seen helium become a solid. It'll become a liquid, but not a solid. With dipole, if we had something like carbon monoxide, what's going to happen is, it's actually a triple bond. You have a positive, negative, partially positive, partially negative. But what that means is a large percent of the time, most of the time, this is the negative end. Most of the time, this is a positive end. That means that a bond forms between there. But even so, when that bond switches from one or the other, then it'll push apart. But it allows there to be connections throughout the whole thing. Get it slow enough, and those connections will form in a permanent way, even though there's temporary disruptions that take place. And then the water molecules, as we mentioned before, or any of these, the difference is that even though it's partially positive, partially negative, when the electrons are with the oxygen, this hydrogen atom disappears and becomes essentially just a little positive blob right on the top, a little positive region right on the top of the oxygen. And that means another oxygen can get real close to that. In fact, my picture here shows these hydrogens as being quite large, but in reality, they would be very, very small. So those are the molecular solids, and they will form very similar crystals to the covalent solids. They just have to happen to have lower melting points, and these will not conduct electricity. Ionic solids will conduct electricity when they're melted and when they are dissolved in water. Molecular compounds, because they're formed from molecules, not ions, will never conduct electricity. Finally, we have what are called atomic solids. And as we said, the constituent part here is the atom. And there's actually two different types of these because there's two different types of atoms. If you take something say the noble gases, they will eventually form solids out of individual atoms. Hydrogen would be a molecule, but if you took neon, eventually you'll get solid neon, and it will form a molecule. But because it's dispersion forces, it'll be a very, very low melting points. You have basically any atom, if you get it cold enough so that the molecules can, actually the atoms can start linking up, will eventually form a solid. And then there are some that are special, like carbon. There's graphite and diamond, but that's beyond what we're going to do. The one that I want to talk about here on the atomic solids is metallic solids. Metallic solids are kind of interesting. And I'm going to erase over here because I just don't have the room. Metallic, we have not talked about yet. We talked about ionic, having a transfer of electrons, covalent bonds, sharing electrons. What's interesting about metallic solids is that if you bring metal atoms together in the same location, they also want to share electrons. But they want to share electrons for a different reason. Non-metals want electrons. Metals want to get rid of electrons. And what we find is if you take, let's say we take a bunch of copper atoms. We'll just put these as copper atoms. Copper atoms have more electrons than they want, and they want to get rid of those electrons. Something very interesting happens when copper atoms get close to each other. their orbitals start overlapping, and they actually don't need as many electrons. That sounds weird, but they actually, in a sense, push their electrons out. And those electrons, so let's say copper has, let's number 29, it has 29 electrons. But every other copper atom that gets closer starts sharing the orbitals, and it doesn't need as many electrons. And you actually end up getting electrons that are detached from their atoms. But they aren't free to just go anywhere. And remember, this is still a positive charge here at the center. But these atoms, electrons, in a sense, are free to move and sort of wander around inside of this, this solid. It turns out that it is the fact that there are all of these electrons, and in fact they will call this a sea of electrons, that is the glue that holds the copper atoms together. They, in a sense, are all sharing each other's electrons. Not to have more, but to have less. But this electron, I just followed one electron. This electron would be doing the same thing, be moving around through here. That sea of electrons is what holds all of the atoms together. It gives metal a lot of its properties. It gives it its luster, its shininess, because those electrons are what is reflecting the light back. It causes, if I put a positive and a negative charge, those electrons will tend to move this direction. We call that an electrical current. It's what allows you to hit a piece of metal and it bends and not breaks, because the atoms aren't really linked like ionic compounds. They're loosely held together, and so they're able to move and adjust. In other words, if I hit this with a hammer, I may move this section down so that it comes down here. We would call that a dent, but those will still be held by those other electrons. There's actually two different types of, well, what's interesting about metals, this would be pure copper, but we can also make what is called an alloy. An alloy is two or more metals that are combined. But what's interesting is all metals have basically the same properties. So if I take copper and zinc and I mix those together, I actually get then brass. And if I intersperse those, and by the way, you don't need 50-50. You could have more copper and less zinc, for instance. You could go like this, so that we have maybe twice as much copper as zinc. We would then have an alloy, but we would have the same thing. Those electrons would move around through there and be shared by all of these, and as a result, we would have a piece of metal, and it would share the properties of both of them. There's also, you can take and put other things inside of there. You could put copper. Let's say we take, not copper, carbon inside of iron. Iron with copper in it is a much stronger, I've forgotten the name, my mind just went blank, but there's a name for that when you put in carbon into iron. And this does the same thing, although carbon doesn't share quite as much, but you'll have the same situation as here. If the two atoms that are making up the metal are close to the same size, we call this a substitutional alloy. And it will basically share the properties of both. Oh, it's called tempered steel. It's steel when it's iron mixed with something else, and then it's tempered. This we call an interstitial alloy. Inter means between, to stand between. This substitution alloy is when the two metals making the alloy are close to the same size. And this one is when two metals or the elements are different size. And we're going to run out of time here on this video. In fact, we're already a little longer than I like to go. But these ones will kind of be a cross between them. So copper and zinc, when you mix them together, have a lot of the properties of copper, a lot of the properties of zinc. These interstitial alloys, inter means between, station means to stand. These copper, in a sense, are standing in between there. And it makes the properties quite different of that particular alloy. I liken it to taking, if I had a bicycle chain and I threw some sand in there. The sand being very small actually gums up the works. It makes it hard for that chain to turn. And that's what's happening here. This copper, if I hit this with a hammer, these carbon atoms don't allow movement the way this would allow movement. So that may be hard to grasp, but they're going to ask what are some differences between interstitial and substitutional alloys. The difference is that the metals are either the similar size or different size, but the difference is interstitial alloys have much different properties than the compounds, the atoms that are making them up, whereas substitutional alloys, the properties are similar to the properties of the two atoms that make those up. What we're going to do for this assignment, we're going to do problems 41 through 50. This is at the end of the chapter, and that finishes up chapter 13. So that's actually the last lesson for this week. We only have 3 lessons. We'll do a little bit of review, and then we have a test that's coming on this. So I'll review some of this on Wednesday of next week as well, because we went through that pretty quick. So